Alright, so we're going to look at how to do question 4 on the electric fields worksheet. This question kind of threw a few people for a loop. I think the most important thing here to do is to draw your diagram. So first we got to know we've got 3 charges. Each charge is 4.0 times 10 to the negative 6 coulombs. And they're fixed to the vertices, which is the corners, of an equilateral triangle whose sides are 20 centimeters long. So let's set that up. So if I got one charge, another charge, another charge, and this is always 20 centimeters. Look at that little line there. That means that they're all the same. Alright, we can kind of do a dotted line and separate it into a 90-degree angle. And why? Well, first of all, we know that all of our angles should be 60 degrees. And of course, if we cut this in half, we're going to get a 30-degree angle up there. This is all just kind of pre-prep work for this question, because we're going to look at each charge individually. So what you need to realize about this question, the most important part is this. I can rotate my equilateral triangle all I want, and it's always going to be the same. I could rotate this charge until it's all the way at the top, and that means this charge has moved over here, and this charge has moved over here. They're all the exact same value, so my triangle isn't going to look any different. What that means is everything is kind of symmetrical in a weird way, and it means the force, although the direction may not be the same, the force felt on each charge will be the same because they're each affecting each other the same. So it's irrelevant which charge I put on top, because I could easily rotate my triangle and have any of the 3 charges on top. Therefore, in solving for one of the charges, for magnitude, I've found all the magnitudes. Then all I need to worry about is direction. So let's go ahead and start looking at that. I'm going to call this Q1, this Q2, and this is Q3. Now, in finding the force felt on charge 1. Alright, that top charge there. In the x direction, meaning the force is felt from charge 2 and charge 3. If you don't believe me, you can go and do the math here, but they're going to cancel out. Whatever the charge is, keeping in mind my distance is 20 centimeters, I could kind of go and say, okay, well, this here is going to be my force between 1 and 3, and so this is going to be here, my force between 1 and 2 on this side. And the x component of that is the cos of the angle. So the cosine of 60 degrees times f(1,3) is going to be the 1 component, and well, we can write that is equal to the cos of 60 degrees times k q1 q3 over 20 centimeters, so 0.2 meters squared. But the other one from charge 2 would be the cos of 60 degrees times f(1,2), which would be equal to the cos of 60 degrees times k q1 q2 over 0.2 meters squared. And if all the charges are the same, then there's no difference between these. They're the exact same value. Hopefully that was kind of made clear here. You wouldn't even have to explain all this in the question. You could just say that because of symmetry, I know that the x component here and the x component here are going to be the same. So this charge, charge 1, is going to be repelled from each of these, meaning it's going to feel one force to the left and one to the right. We have 2 equal forces in opposite directions. I know now, without doing any math, that the sum of my x forces is 0. Now in the y direction, we have to look at it a little bit differently. Kind of zoom up on one of these triangles here on the side. This is Q1. It's my 20 centimeters. Here's Q3. This is 60 degrees. We're looking for this part here. This is our Y component. So we want to use the sine of 60 degrees times the force between charge 1 and 3, which is equal to the sine of 60 degrees times K Q1 Q3 over my separation 0.20 meters squared. Plugging in all my numbers here, this is the sine 60 degrees times K, so 9.0 times 10 to the 9 times my first charge, 4.0 times 10 to the negative 6 coulombs times my second charge, 4.0 times 10 to the negative 6 coulombs. All the charges are the same. It states that in the question. Each with a charge of 4.0 times 10 to the negative 6 coulombs divided by 0.20 meters squared is equal to, running this through, you get 3.12 newtons. And let's check the direction of this. Okay. This charge up here is repelled from this charge, so it wants to move away from it. So in the y direction, that constitutes up. This charge really wants to move to the left and up. We're only talking about the y direction here, so keep in mind up. Now, the force felt from charge 2, by, again, an argument for symmetry, we would run through all the exact same math, and we would end up with the same value for a force, 3.12 newtons, and also up. So the sum of our y forces is going to be equal to the force from 1 and 3 in the y direction plus the force from between charges 1 and 2 in the y direction, which is equal to 3.12 newtons plus 3.12 newtons equals 6.24 newtons. So we now know that at the top of that triangle we would have our force is equal to 6.24 newtons up, because we have no x force at all, so we don't even have to go making any triangle. We just know that that is the entire force. So that's part A pretty much done. We know that on charge 1 the whole force is 6.24 newtons up. Now, going back to that argument I made at the beginning, the charge or the force on charge 2 and charge 3 are also 6.24 newtons, but they're not up. It doesn't make sense for all three of these charges to want to move up. They all want to repel each other. So the key here is to draw your diagram kind of nicely. So I'm going to kind of work on that. Q1, Q3, Q2. Okay. And this was my force from 1 on charge 1. Alright, so what's important to notice here is that we could just as easily have defined our triangle as having this be the 90-degree angle. So just kind of to show you, if I rotate my page enough, that becomes the top of the triangle. In which case, my force would be out this way. If we want to find what that angle is, we can just continue our horizontal line from here, and by an argument of geometry, these two lines are the same. These angles, sorry, are the same angles. So if we look back at our triangle, this cuts this full angle right in half. The angles of each of these are 60 degrees. So this half is 30. So this half is 30. So we now know that the force on charge 2 is 6.24 newtons at, let's actually, I'm actually going to use compass headings on this just for simplicity's sake. So this would be at west, 30 degrees south. Now, last part of this is to look at the third charge. Again, we can kind of just mirror what we know already. There's a lot of geometry in this question. Alright, you can do each of these by finding the x and the y components at each place, but you're going to be doing a lot of work doing that. This geometry is meant just to cut a lot of your work in half. So again, we know that the force now on charge 3 is also 6.24 newtons. But the angle's going to be, again, a little different. It's going to be 30 degrees east, 30 degrees south. And that's all based on our geometry. All we had to do was solve the first one, the force on charge 1, which is pretty much most of our calculation work. Everything up to this point was for charge 1. And then all of this was all we needed for finding the second and third charge based on some principles of geometry. And that's how you do question 4.